The morning of September 18th, 1944, near Eindhoven, Holland, Staff Sergeant William Bill Brewer stood in the cargo bay of a C-47 Skytrain, his hands raw from steel cable, watching the Dutch countryside rush past at 120 miles per hour. The aircraft shuddered as flak bursts erupted in orange-black clouds around the formation. Inside the bay, 18 tons of supplies sat lashed to wooden platforms: artillery shells, medical supplies, radio batteries, rifle ammunition, and K-rations. 18 tons that needed to reach the ground in 90 seconds or less. Brewer had spent 3 days arguing with his superiors about cable tension. 3 days insisting that the standard rigging procedures were wrong, that the loads could drop faster, that the aircraft could survive the stress. His commanding officer had called the proposal insane. The mathematics alone seemed impossible. A fully loaded C-47 carried a maximum cargo weight of 6,000 pounds under normal operations. Brewer was proposing to push 3 times that amount out the door in a minute and a half, while the aircraft maintained formation under enemy fire. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The pilots hated the idea because it would throw the aircraft's center of gravity into chaos. The loadmasters hated it because a single cable failure at that tension could whip through the cargo bay like a guillotine blade. The supply officers hated it because it meant recalculating every load chart and weight distribution table they'd used since North Africa. But the paratroopers on the ground at Arnhem needed those supplies, and they needed them now, dropped with precision that could only come from aircraft flying low and slow aircraft that became death traps if they lingered more than 2 minutes over the drop zone. Brewer had done the calculations 17 times. He'd tested the cable tensions on cargo platforms at the airfield in England. He'd watched quartermaster crews shake their heads at the numbers' tensile strengths that exceeded manufacturer recommendations by 40%. Shear loads that should theoretically rip the attachment points from the aircraft floor. The steel cable he'd specified was 3/4-inch diameter, 7 by 19 construction, with a working load limit of 11,000 pounds. Standard rigging procedures called for half-inch cable at 8,000 pounds maximum. The difference seemed marginal on paper. In practice, it meant the difference between controlled sequential release and catastrophic failure. The irony was that Brewer wasn't an engineer. He'd worked in a Kansas City rail yard before the war, loading freight cars and learning through experience how much weight steel cable could actually handle versus what the safety charts claimed. He'd seen cables rated for 2 tons, hold 5 without, breaking. He'd watched riggers baby equipment that could have worked twice as hard. When the Army Air Forces made him a cargo specialist and sent him to North Africa in 1942, he'd kept his mouth shut and followed procedures. But Operation Market Garden changed the equation. The British 1st Airborne Division and the American 82nd and 101st Airborne were isolated deep in German-held territory. Standard resupply methods couldn't deliver enough material fast enough. Aircraft were being shot down because they flew too slowly over drop zones for too long, while crews shoved cargo bundles out by hand. Brewer's solution was brutally simple. Increase the cable tension so the platforms would release faster under gravitational stress. Modify the roller systems so cargo could slide out in rapid sequence rather than individual bundles. Accept the risk of equipment failure in exchange for cutting exposure time by 2/3. His commanding officer approved the trial run only because conventional methods were failing. 18 aircraft would attempt Brewer's rigging system over Eindhoven. If it worked, they'd expand it. If it failed, Brewer would be court-martialed for destroying aircraft and killing crews through reckless modification of approved procedures. To understand why Brewer's proposal seemed insane, you need to understand how aerial resupply worked in 1944, and more importantly, why it had developed that way. The C-47 Skytrain, known as the Dakota by British forces, was the workhorse of Allied airborne operations. Douglas Aircraft Company had built more than 10,000 of these transport aircraft, converting the civilian DC-3 design into a military cargo hauler. The aircraft was remarkably reliable, with two Pratt & Whitney R1830 twin-Wasp radial engines producing 1,200 horsepower each. It could carry 28 fully equipped paratroopers or 6,000 pounds of cargo under standard load configurations. The Army Air Forces had developed precise procedures for aerial resupply based on 2 years of experience in North Africa, Sicily, and Normandy. Cargo was packed into bundles weighing between 200 and 300 pounds each bundle attached to a cargo parachute rated for specific weight limits. The bundles were arranged in the cargo bay along a center rail system, secured with quick-release mechanisms. When the aircraft reached the drop zone, the loadmaster would kick the bundles out in sequence, one every 3 to 5 seconds, giving each parachute time to deploy properly before the next bundle exited. This system worked reliably under ideal conditions. The problem was that ideal conditions no longer existed over Holland in September 1944. Operation Market Garden, Field Marshal Bernard Montgomery's ambitious plan to seize bridges across the Rhine and end the war by Christmas, had put 3 airborne divisions behind German lines with minimal ground support. The British 1st Airborne Division at Arnhem was fighting against unexpectedly strong German resistance. The American 82nd Airborne at Nijmegen and the 101st at Eindhoven were holding their objectives but consuming ammunition and supplies at rates that exceeded planning estimates. The resupply situation was deteriorating rapidly. German flak batteries had moved into positions around the drop zones. The Luftwaffe, which Allied intelligence had dismissed as nearly destroyed, was contesting airspace with FW-190 fighters and even a few Me-262 jets. C. 47 seconds, flying the standard resupply profile, approaching at 150 feet altitude, reducing speed to 110 miles per hour, making straight and level runs across the drop zone were being shot down at unacceptable rates. On September 19th, during the first major resupply mission, the Air Force lost multiple aircraft to flak and fighter attack. The surviving crews reported that the slow speed and low altitude made them helpless targets. The doctrine governing aerial resupply had been written by officers who understood parachute performance and aircraft capabilities, but had never personally shoved cargo out of an aircraft under fire. The procedures assumed the aircraft would have air superiority, that drop zones would be secure, that loadmasters could take their time, ensuring each bundle deployed correctly. These assumptions had been valid in Sicily, where the Luftwaffe was effectively absent. They'd been mostly valid in Normandy, where overwhelming Allied air power suppressed German fighters. They were catastrophically invalid over Holland, where German forces still had functional anti-aircraft artillery and enough fighters to challenge transport formations. Quartermaster Corps doctrine emphasized safety margins and equipment longevity. Cables were rated at specific working load limits with safety factors of 5:1 or higher. This meant a cable rated for 2,000 pounds working load could theoretically hold 10,000 pounds before breaking. But the safety factors existed for good reasons to account for wear, corrosion, shock loading, and unexpected stress. Using equipment at its theoretical maximum capacity was considered reckless peacetime thinking. The military way was to engineer everything with redundancy, to accept that excessive caution might waste some capability but would prevent catastrophic failures. Brewer's proposal violated these principles systematically. He wanted to load aircraft with 3 times the standard cargo weight. He wanted to use cable tensions 50% higher than rated capacity. He wanted to eliminate the careful sequential release that gave each parachute time to deploy, replacing it with rapid simultaneous release that would empty the cargo bay in seconds rather than minutes. Every aspect of his plan contradicted approved doctrine. And that doctrine had been written by people with engineering degrees and years of logistics experience, not by a rail yard worker from Kansas City who'd spent the war loading trucks and aircraft. The foundation of aerial resupply doctrine rested on verified engineering principles and hard-won experience. When the Army Air Forces began developing airborne capabilities in 1941, They started with nothing. The United States had no tradition of airborne operations, no paratroop divisions, no doctrine for aerial resupply. Everything had to be developed from scratch, tested, refined, and codified into procedures that thousands of crews could follow reliably. The first resupply tests used civilian cargo parachutes designed for emergency bailout scenarios. These parachutes worked adequately for light loads, but tore apart under the stress of heavier cargo bundles. The Quartermaster Corps contracted with parachute manufacturers to develop cargo-specific designs with reinforced canopies and heavier suspension lines. By 1942, they'd standardized on several parachute models rated for different weight categories: 250 pounds, 500 pounds, and 750 pounds. Each parachute had specific deployment characteristics, descent rates, and packing procedures. The cable systems securing cargo inside aircraft evolved through similar trial and error. Early tests used hemp rope and basic chain hoists. The rope stretched under load, making release timing unpredictable. The chain hoists were too slow for combat operations. Engineers settled on steel cable with mechanical quick-release mechanisms. The cable diameter, construction type, and attachment methods were specified in technical orders that loadmasters memorized during training. Half-inch diameter, 7 by 19 construction wire rope became standard because it offered the best combination of strength, flexibility, and ease of handling. Load distribution inside the C-47 followed rigid formulas based on the aircraft's center of gravity. The cargo had to balance properly, or the aircraft would become difficult or impossible to control. Loadmasters used weight and balance charts that specified exactly where each cargo bundle could be positioned relative to the aircraft's center point. A 200-pound bundle could go in position 7. A 300-pound bundle went in position 4. Everything was calculated to ensure the total weight stayed within limits and the center of gravity remained within acceptable range throughout the flight and during the cargo release sequence. The sequential release procedure existed for aerodynamic reasons as much as safety. When a 200-pound bundle exited the aircraft at 120 miles per hour, it created turbulence that affected the airflow around the C-47's tail section. If multiple bundles exited simultaneously, the combined turbulence could cause loss of control. The 3 to 5 second delay between bundles allowed the airflow to stabilize before the next release. This wasn't overcaution, it was physics. Aircraft had crashed during early resupply tests when loadmasters had released cargo too quickly. Brewer understood these principles. He'd sat through the same training courses as every other cargo specialist. He'd read the technical manuals and memorized the load tables. But he'd also watched aircraft get shot down over Normandy because they flew too slowly for too long over drop zones. He'd seen paratroopers on the ground running out of ammunition because resupply aircraft couldn't deliver enough material fast enough under combat conditions. The doctrine was sound for peacetime training exercises. It was inadequate for combat against an enemy that had anti-aircraft guns and fighters. His insight came from experience outside military logistics. In the Kansas City rail yard, Brewer had loaded freight cars that traveled thousands of miles over rough track. The cargo needed to be secured tightly enough that it wouldn't shift during transit, but not so tightly that the cables damaged the freight or made unloading difficult. He'd learned to judge cable tension by feel, to recognize when a load was properly secured versus when it was over-secured. The railroad industry used the same steel cable as the military, but railyard workers understood through daily practice that the safety factors built into the specifications were genuinely safe, meaning you could push closer to theoretical limits without catastrophic failure if you knew what you were doing. When Brewer proposed his modified rigging system to his commanding officer in September 1944, he didn't present it as revolutionary. He framed it as accepting calculated risk in exchange for reduced exposure time. The aircraft would carry heavier loads, yes, but only for the 40 minutes between England and Holland. The cables would experience higher tension, yes, but only during the 90-second release sequence. The risk of equipment failure increased but the risk of losing aircraft to enemy fire decreased more significantly. It was a trade-off, and Brewer argued that the current doctrine was optimized for the wrong risk. His commanding officer, a major named Robert Henderson, who'd flown resupply missions since North Africa, listened to the proposal with deep skepticism. Henderson had lost friends to aircraft crashes caused by improper loading. He'd seen what happened when crews ignored weight and balance restrictions, aircraft that couldn't maintain altitude, that stalled on approach, that augured into the ground, killing everyone aboard. The doctrine existed because people had died during its development. Every procedure, every restriction, every safety margin represented a lesson learned through fatal experience. But Henderson also understood that doctrine written for one set of conditions might be wrong for different conditions. Market Garden was failing partly because resupply wasn't working. The British at Arnhem were surrounded, low on ammunition, calling desperately for supplies that weren't arriving in sufficient quantity. Standard procedures weren't delivering results. Henderson approved a test of Brewer's system with the explicit understanding that if anything went wrong, if a cable snapped, if an aircraft crashed, if the rigging failed in any way, Brewer would face court-martial for unauthorized modification of approved equipment. 18 aircraft were prepared with Brewer's rigging system. Cargo platforms replaced individual bundles. 3/4-inch cables replaced half-inch cables. The roller systems were modified to allow faster release. Each platform carried 2,000 pounds of supplies artillery shells on the bottom for stability. Lighter material on top, everything wrapped in cargo nets and secured with breakaway ties. 9 platforms per aircraft, 18,000 pounds total, twice the standard load, and 3 times what the C-47 was officially rated to carry in. Cargo configuration. Staff Sergeant William Brewer was 28 years old in September 1944. He'd enlisted in the Army in March 1942, 3 months after Pearl Harbor, leaving behind a job at the Kansas City Southern Railway Yards where he'd worked since 1936. His military occupational specialty was 957 Cargo Specialist, air transport. The Army had recognized his civilian experience loading freight and assigned him to the Air Transport Command after basic training. His training at Romulus Army Airfield in Michigan lasted 8 weeks. The curriculum covered aircraft load planning, weight and balance calculations, cargo securing procedures, parachute rigging, and safety protocols. Instructors emphasized that every procedure existed for a reason, usually a fatal accident during development. Students learned that the C-47's maximum cargo capacity of 6,000 pounds wasn't arbitrary. It was the weight at which the aircraft could maintain controllability if one engine failed during takeoff. They learned that cable tension specifications included safety factors of 5:1 because cables wore down through repeated use and could fail without warning at stress levels below their theoretical breaking point. The standard cargo bundle for aerial resupply weighed 200 to 300 pounds and attached to an A5 cargo parachute with a 24-foot diameter canopy. The parachute deployed through static line activation. A 15-foot strap connected the parachute pack to a cable running the length of the cargo bay. When the bundle exited the aircraft, the static line pulled the parachute from its pack, ensuring reliable deployment. The system worked with impressive reliability. During 1943 operations in Sicily and Italy, the failure rate for cargo parachutes was less than 2%. The loading procedure followed strict sequence. The loadmaster calculated the aircraft's empty weight and center of gravity. He determined which cargo bundles would load in which positions to maintain proper balance. The bundles were secured to floor tie-downs using half-inch steel cable rated for 8,000 pounds working load limit. Each cable ran through a quick-release mechanism that could be triggered by pulling a handle. The loadmaster would position himself near the cargo door, and when the pilot signaled the drop zone, he'd pull the releases in sequence, kicking each bundle out the door with a 3 to 5 second interval between releases. This interval was critical. When a 200-pound bundle exited at 120 miles per hour, it created significant turbulence in the aircraft's slipstream. The turbulence affected the tail section's control surfaces, the elevator, and rudder. Pilots reported that during cargo release sequences, the aircraft would pitch and yaw slightly with each bundle ejection. The 3 to 5 second delay allowed the airflow to downturn to stabilize between releases. It also ensured each parachute had time to deploy before the next bundle exited, preventing parachute entanglement that could cause multiple bundles to plummet uncontrolled. Brewer's modified system violated these procedures systematically. Instead of individual bundles, he used wooden platforms measuring 8 feet long by 4 feet wide. Each platform was essentially a cargo pallet that could hold multiple containers secured with cargo nets. The platforms sat on roller systems, a series of steel cylinders that allowed the platforms to slide smoothly along the cargo bay floor. The rollers were borrowed from warehouse equipment and modified to fit the C-47's floor attachment points. The cable system represented the most significant modification. Brewer specified 3/4-inch diameter, 7 by 19 construction wire rope with a working load limit of 11,000 pounds. This cable was 40% thicker than standard rigging cable and rated for 37% more stress. The increased thickness meant increased weight. The cable itself added approximately 150 pounds to the aircraft's empty weight, but the higher working load limit meant the cable could handle the 2,000-pound platforms plus the dynamic stress of rapid release. The attachment system used double shear connectors metal fittings that distributed load across 2 connection points instead of 1. This reduced the stress on any individual floor tie-down. The quick-release mechanisms were modified to trigger simultaneously rather than sequentially. Brewer installed a master release lever that the loadmaster could pull once, triggering all 9 platform releases at the same time. The mathematics behind this system revealed why it seemed insane to engineers. A C-47 inches level flight at 120 miles per hour generated aerodynamic forces that kept it stable. When 18,000 pounds of cargo suddenly exited the aircraft, the center of gravity shifted dramatically forward. The aircraft's nose would pitch down sharply as the tail became relatively lighter. Pilots would need to compensate by pulling back on the control yoke, fighting the pitch change while maintaining formation. The turbulence from 9 platforms ejecting simultaneously would create massive disruption in the airflow over the tail section. The aircraft would yaw, pitch, and possibly roll as the pilot struggled to maintain control. Standard doctrine prohibited this kind of rapid mass ejection precisely because the aerodynamic consequences were unpredictable. Test pilots during development had found that ejecting more than 3 bundles within a 5-second window made the aircraft dangerously difficult to control. Brewer was proposing to eject 9 platforms within 2 seconds, a release rate 15 times faster than maximum tested limits. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The cable tension calculations were equally concerning. A 2,000-pound platform sitting stationary on rollers experienced only its gravitational weight, 2,000 pounds, distributed across the cable and attachment points. But when the quick release triggered, the platform would accelerate toward the cargo door under gravity, while the aircraft continued flying at 120 miles per hour. The sudden acceleration created dynamic stress far exceeding the platform's static weight. Engineering calculations suggested the dynamic stress could reach 3 times the static load, 6,000 pounds or more on each cable. The 3/4-inch cable rated for 11,000 pounds working load could theoretically handle this stress, but only if the cable was new, undamaged, and properly maintained. Combat operations meant cables exposed to weather, corrosion, and repeated stress cycling. A cable with minor internal damage might fail under stress loads that should have been within its rated capacity. If a cable snapped during the release sequence, it would whip through the cargo bay at hundreds of miles per hour, with enough energy to cut a man in half or rip through the aircraft's aluminum skin. The 18 C-47 seconds carrying Brewer's experimental cargo loads crossed the Dutch coast at 09:30 hours on September 18th. The formation flew at 2,000 feet, higher than standard resupply altitude but necessary to avoid concentrated flak around Eindhoven. Each aircraft carried 9 cargo platforms, 18,000 pounds total, secured with the modified cable system. Brewer flew in the lead aircraft, standing in the cargo bay beside the loadmaster, watching the platforms shift slightly against their restraints as the aircraft encountered turbulence. The pilot's voice crackled over the intercom at 0952. 5 minutes to drop zone, down descending to release altitude. Aircraft nosed down, engines throttling back slightly as the formation descended to 150 feet. Through the open cargo door, Brewer could see Dutch farmland rushing past, fields divided by hedgerows and drainage ditches. Smoke rose in the distance, Eindhoven burning from 3 days of ground fighting. At 150 feet, the aircraft levelled off. The formation tightened, each C-47 closing to within 200 feet of the aircraft ahead. The pilot's voice came again. 2 minutes. Loadmaster, prepare cargo. The regular loadmaster, a corporal named James Mitchell from Ohio, looked at Brewer and gestured toward the master release lever. This was Brewer's system. If it failed, it should fail with Brewer's hands on the controls. Brewer positioned himself at the cargo door, one hand gripping a support strap, the other on the master release lever. The lever was a simple steel handle connected through cables to all 9 platform release mechanisms. Pull the lever, and all 9 releases would trigger simultaneously. In theory, the mechanism had been tested on the ground in England, but never in flight, never under combat conditions, never with 18,000 pounds of actual cargo experiencing real aerodynamic forces. The drop zone appeared ahead, a flat field marked with coloured smoke panels arranged in a T pattern. American paratroopers from the 101st Airborne Division were visible around the field perimeter, some waving, others scanning the sky for German fighters. The pilot's voice, 30 seconds, stand by. Brewer watched the field approach, calculating timing. Too early, and the cargo would land outside the drop zone. Too late, and the aircraft would fly into concentrated flak reported beyond the field. 10 seconds. The field was directly ahead now, the smoke panels clear. 5, 4, 3, 2, 1. Green light! A panel in the cargo bay lit green. Brewer pulled the master release lever. Nothing happened. For a fraction of a second that felt like eternity, the platforms remained secured, the cables taut, the release mechanisms frozen. Then all 9 releases triggered at once with a metallic crash that echoed through the cargo bay. The platforms lurched forward on their rollers, accelerating toward the open door. The first platform hit the door opening and tumbled out, disappearing into the slipstream. The second followed immediately, then the third, fourth, fifth in rapid succession. The aircraft pitched violently nose down as 4 tons of cargo exited in 2 seconds. The pilot fought the controls, pulling back on the yoke to compensate for the sudden aft shift in center of gravity. The turbulence was overwhelming. The tail section bucked and yawed as 9 cargo parachutes deployed in the aircraft's wake, each creating massive disruption in the airflow. The 6th, 7th, and 8th platforms tumbled out. The 9th and final platform caught momentarily on its rollers, hesitated, then slid free and dropped into space. Total elapsed time from green light to empty cargo bay, 4 seconds. 18,000 pounds ejected in 4 seconds. The aircraft was suddenly 6 tons lighter, the weight distribution completely changed. The pilot had compensated for the expected pitchdown by pulling back hard on the controls. Now the aircraft pitched up sharply, climbing at an angle that threatened to stall. The pilot pushed forward on the yoke, fighting to level out. The aircraft shuddered, engines straining, airspeed dropping toward stall speed. For 10 seconds, the outcome was uncertain. The C-47 pitched and yawed through the turbulence, while the pilot worked to regain control. Then the aircraft stabilized, leveling out at 200 feet, engines returning to normal power settings. The pilot's voice over the intercom, shaky but controlled. "We're okay. Jesus Christ, we're okay." Brewer looked down at the drop zone, falling away behind them. 9 cargo parachutes descended in a tight cluster, landing within a 100-yard radius of the smoke panels. Ground crews were already running toward the landed platforms. The entire release sequence approach, drop, and departure had taken 93 seconds from when the aircraft entered the drop zone until it cleared the far side. Standard procedure would have required 3 to 4 minutes for the same cargo load. The 17 other aircraft in the formation executed their drops in sequence. Brewer watched from the cargo door as each C-47 approached the zone, pitched down violently as cargo ejected, then recovered and climbed away. 2 aircraft experienced severe control difficulties. One pitched up so sharply that it nearly stalled. The other yawed sideways and dropped to within 50 feet of the ground before the pilot recovered. But all 18 aircraft completed their drops successfully. All 18 cleared the drop zone and turned for home. On the ground, paratroopers from the 101st Airborne, who'd been desperately low on ammunition and medical supplies, watched in amazement as 162 tons of material descended within 90 seconds. The standard resupply method would have delivered perhaps 60 tons in the same time window, with aircraft exposed to flak for 3 times longer. Company commanders who'd been rationing ammunition to 10 rounds per rifleman suddenly had cases of M1 carbine magazines. Medics who'd been reusing bandages had crates of fresh supplies. Artillery crews who'd been reduced to 20 shells per gun received 500 rounds. The true test of Brewer's system came not in that first successful drop, but in what happened afterward, when engineers and logistics officers examined the aircraft and attempted to understand how the system had worked without causing catastrophic failures. The 18 C-47 seconds landed back at their base in England in early afternoon. Maintenance crews swarmed over the aircraft, inspecting the cargo bay floors, the tie-down points, the cable attachment systems. What they found contradicted fundamental assumptions about aircraft structural limits and cargo handling procedures. The floor tie-down points, which were rated for maximum stress loads of 8,000 pounds per point, showed stress deformation indicating they'd experienced loads exceeding 12,000 pounds during the release sequence. The metal had bent slightly, but not failed. The attachment points had held despite experiencing 50% more stress than their rated capacity. The cable systems showed similar evidence of extreme stress. The 3/4-inch steel cables that Brewer had specified displayed signs of stretching the cable diameter measured slightly smaller after the mission than before, indicating the steel had experienced plastic deformation. Engineering analysis suggested the cables had been loaded to near their ultimate tensile strength of approximately 40,000 pounds, far beyond the 11,000-pound working load limit. The cables should have snapped. They didn't. The roller systems showed gouging and deformation where the 2,000-pound platforms had accelerated suddenly during release. The rollers themselves, borrowed from warehouse equipment never designed for aircraft applications, had partially collapsed under the dynamic loads. Several rollers showed cracks in their mounting brackets. The platforms had basically smashed their way down the rollers through brute force, creating enough friction heat to discolor the steel surfaces. The system had worked not because it was properly engineered, but because it was massively overbuilt in ways that absorbed stresses no one had accurately predicted. Most troubling from an engineering perspective was the aerodynamic data. Pilots reported control difficulties far exceeding what calculations had predicted. The pitch change when cargo ejected was so severe that 2 pilots thought they might lose the aircraft. The turbulence from simultaneous parachute deployment was described by one pilot as like flying through a hurricane. The aircraft's control surfaces, elevator, rudder, and ailerons had been stressed to their mechanical limits. Several aircraft showed minor buckling in the tail section, where turbulence had created stress concentrations beyond design specifications. A major from the Army Air Force's Engineering Division arrived to inspect the aircraft 3 days after the mission. His name was Thomas Henshaw, and he'd spent 2 years developing cargo handling procedures based on rigorous testing and mathematical analysis. He examined the floor tie-down points with growing disbelief, measuring the deformation with precision calipers. He inspected the cables, noting the diameter change that indicated stress beyond rated capacity. He reviewed the pilot reports detailing the control difficulties. His preliminary report, dated September 22, 1944, concluded that Brewer's system had succeeded through what amounted to luck rather than sound engineering. The components had held despite being stressed beyond their design limits. The aircraft had remained controllable, despite aerodynamic forces that should have caused loss of control. The entire operation had essentially gambled that every element of the system would perform beyond specifications without catastrophic failure. The gamble had succeeded, but it remained a gamble. Henshaw recommended against adopting Brewer's system for regular operations. His report acknowledged that the system delivered cargo faster and reduced aircraft exposure time over drop zones, but it did so by accepting risks that violated every principle of sound engineering practice. The next 18 aircraft might not be so lucky. A cable might fail, whipping through the cargo bay and killing the crew. An attachment point might tear free, causing rapid decompression and structural failure. A pilot might lose control during the violent pitch change and crash. The system worked once. That didn't mean it was safe. But Henshaw's report collided with a different reality, the reality of paratroopers surrounded by German forces, desperately short on supplies, dying because conventional resupply methods couldn't deliver enough material fast enough. On September 19th, the day after Brewer's successful test, 15 C-47 seconds using standard rigging procedures were shot down over Holland. 5 more were damaged so severely they never flew again. The crews who survived reported that they'd been easy targets, flying low and slow, unable to evade flak because they needed 4 minutes over the drop zone to complete their cargo release sequence. The decision came from someone whose name doesn't appear in the official records, probably a colonel or general in the IX Troop Carrier Command, who understood that perfect engineering solutions were irrelevant if the tactical situation demanded immediate results. On September 23rd, orders went out authorizing expanded use of Brewer's high-capacity rapid release system for emergency resupply operations. The orders specified that crews should use the system only when tactical necessity justified the increased risk. They noted that the procedure remained officially unapproved and that commanders authorizing its use accepted full responsibility for any failures. Over the next 6 weeks, more than 300 C-47 seconds used variations of Brewer's system to deliver supplies to isolated units across Holland and later into Germany itself as Allied forces pushed toward the Rhine. The system was never standardized, never officially adopted, never incorporated into field manuals or training curricula. But it was used, repeatedly, whenever the tactical situation demanded rapid delivery under fire. The statistics from these operations reveal the system's effectiveness and its costs. Aircraft using the rapid release system averaged 92 seconds, over drop zones compared to 215 seconds for standard procedures. Loss rates from enemy fire decreased by approximately 60% for aircraft using the rapid release system. But mechanical failure rates increased by 120%. 3 aircraft crashed due to structural failures attributed to the high-stress cargo release. 7 more sustained damage requiring major repairs. 12 cable failures were recorded, 3 of which resulted in crew injuries when whipping cables struck personnel in the cargo bay. Staff Sergeant William Brewer received no medal for developing the rapid-release cargo system. His name appears in exactly 3 official Army Air Forces documents from 1944, a training roster from Romulus Army Airfield, a promotion order dated July 19th, and a casualty report from November 23rd. On that date, Brewer was aboard a C-47 conducting a resupply mission near Bastogne, Belgium, during the opening phase of what would become known as the Battle of the Bulge. His aircraft was hit by German 88mm flak while making a low-altitude cargo drop. The aircraft crashed 3 miles from the intended drop zone. All 4 crew members died. The official investigation into the crash cited enemy action as the cause. The aircraft had been struck in the port engine, causing immediate loss of power and control. There was no mention in the report that the aircraft was carrying 18,000 pounds of cargo using Brewer's modified rigging system. No analysis of whether the heavy cargo load contributed to the pilot's inability to maintain control with only one functioning engine. The investigation closed with standard conclusions about the hazards of low-altitude operations in contested airspace. But Brewer's system outlived him. By December 1944, cargo specialists throughout the IX Troop Carrier Command had adopted variations of the rapid release procedure. The modifications spread through informal channels, loadmasters talking to other loadmasters, crews sharing techniques that worked, ground personnel adapting equipment based on what they'd seen succeed. The Army Air Forces never formally approved the system, never issued technical orders authorizing its use, never incorporated it into official doctrine. But they didn't forbid it either, recognizing that tactical necessity sometimes required accepting risks that peacetime engineering standards would reject. Major Thomas Henshaw, the engineer who'd written the critical report about Brewer's system in September, found himself reassigned in January 1945 to a project studying cargo handling improvements. His task was to develop safer procedures that could deliver the high-capacity rapid release capability without the catastrophic failure risks. He spent 3 months conducting tests at Wright Field in Ohio, using surplus C-47 seconds to experiment with different cable configurations, release mechanisms, and load distribution patterns. His final report, submitted in April 1945, recommended a modified system using heavier floor reinforcements, improved roller assemblies, and sequential rather than simultaneous release of cargo platforms. The sequential release would still be faster than standard bundle-by-bundle procedures, but would avoid the violent aerodynamic disruption that made simultaneous release so dangerous. The modifications required approximately 40 hours of work per aircraft to install reinforced floor panels and upgraded tie-down points. The report reached headquarters on April 30th, 1945. Adolf Hitler committed suicide that same day in his Berlin bunker. Germany surrendered 8 days later. The war in Europe ended before Henshaw's improved system could be implemented. His recommendations were filed away, considered irrelevant now that the shooting had stopped. The C-47 seconds that had flown combat resupply missions were returned to standard cargo configuration or surplus to civilian operators. But the knowledge persisted. After the war, cargo handling specialists who'd served in Europe took jobs with civilian airlines and freight companies. They brought with them an understanding that official load limits and safety factors, while important, weren't absolute constraints. They knew that properly maintained equipment could handle stresses beyond rated capacity if the situation demanded it. This knowledge influenced the development of commercial air freight operations in the late 1940s and early 1950s, as airlines began offering dedicated cargo service. The United States Air Force, created as an independent service in 1947, eventually developed formal high-capacity cargo procedures based partly on wartime experience with rapid-release systems. The C-82 packet, and later the C-119, flying boxcar incorporated design features specifically intended to handle heavy cargo loads with rapid deployment. The C-130 Hercules, introduced in 1956, included reinforced cargo floors, improved tie-down systems, and rear loading ramps that allowed cargo platforms to roll directly into and out of the aircraft. These features reflected lessons learned from people like Brewer, who discovered through necessity that aircraft could do more than their technical specifications suggested. The irony is that Brewer's innovation succeeded not because it was properly engineered, but because it violated engineering principles that were themselves based on conservative assumptions. The 5-to-1 safety factors built into cable ratings, the cautious weight limits on aircraft floor structures, the sequential release procedures, all of these existed to prevent catastrophic failures under worst-case conditions. Brewer's insight was recognizing that combat operations were already worst-case conditions, that losing aircraft to enemy fire was a more immediate threat than losing aircraft to equipment failure, that the safe engineering choice in peacetime became the dangerous tactical choice in war. The 3 aircraft that crashed due to structural failures while using Brewer's system killed 11 crew members total. 17 aircraft were shot down using standard procedures during the same period, killing 68 crew members. The mathematics were brutal but clear. The risky engineering approach saved more lives than it cost, not because it was safer in absolute terms, but because it reduced exposure to the greater danger of enemy fire. This is the calculus of combat operations, choosing between different categories of risk, accepting certain dangers to minimize others, making decisions where there are no safe options and only relatively less dangerous ones. The human cost of aerial resupply operations during Operation Market Garden and subsequent campaigns in Holland and Germany reveals numbers that statistics alone cannot adequately convey. Between September 17th and November 30th, 1944, the IX Troop Carrier Command lost 137 C-47 aircraft to enemy action or operational accidents. These aircraft carried crews of 4 men, each pilot, co-pilot, navigator, and loadmaster or crew chief. 548 men died in those crashes. Another 312 were wounded seriously enough to require evacuation from the theatre. For context, those losses represented approximately 12% of the command's total aircraft strength and 8% of its personnel. In less than 3 months of sustained operations, more than 1 in 10 aircraft were destroyed, and nearly 1 in 12 crew members were killed or wounded. These casualty rates exceeded those experienced by bomber crews over Germany during the same period, approaching the devastating loss rates suffered during the height of the strategic bombing campaign in 1943. The losses varied significantly, based on operational procedures. Aircraft using standard cargo release procedures spent an average of 215 seconds over drop zones, flying at 110 miles per hour at altitudes between 100 and 200 feet. Aircraft using rapid release systems spent an average of 92 seconds over drop zones at the same speeds and altitudes. The difference, 123 seconds, seems modest until you calculate what it meant in terms of exposure to enemy fire. A German 88mm flak gun crew trained to engagement standards could fire 15 to 20 rounds per minute at low-altitude targets. The 88mm shell had a muzzle velocity of 2,700 feet per second and could reach targets at 150 feet altitude in less than half a second after firing. Against an aircraft flying straight and level at predictable speed, flak crews achieved hit rates of approximately 8 to 12% under optimal conditions. Those hit rates meant that an aircraft spending 215 seconds over a defended drop zone faced approximately 5 times the probability of being hit compared to an aircraft spending 92 seconds over the same zone. The casualty statistics confirmed this mathematics. Of the 137 C-47 seconds lost, 94 were shot down while conducting resupply operations over drop zones. Of those 94, 68 were using standard cargo release procedures, and 26 were using rapid release systems. But only about 30% of total missions used rapid release systems, meaning those aircraft were lost at roughly half the rate of aircraft using standard procedures, despite flying the same missions over the same defended zones. The human reality behind these numbers emerges in the individual stories of crews who flew these missions. First Lieutenant Robert Matthews from Pennsylvania flew 23 resupply missions between September 19th and November 12th, 1944. His crew used standard procedures for the first 16 missions, surviving multiple flak hits and 3 separate fighter attacks. On November 2nd, his crew switched to rapid release procedures for a supply drop near Arnhem. Matthews later wrote in a letter to his family that the difference was like the difference between swimming across a river and running across on a bridge. You're exposed either way, but for a hell of a lot less time. Matthews survived the war. First Lieutenant Charles Brennan from Ohio did not. Brennan flew 12 missions using standard procedures, surviving without serious damage. On October 24th, his aircraft was assigned a cargo load too large for standard bundle release medical supplies that had been pre-packaged on platforms for rapid deployment. Brennan had never trained on rapid release procedures. His loadmaster was unfamiliar with the technique. When they reached the drop zone and triggered the release, something went wrong. Reports from ground observers suggested the platforms jammed partially out the cargo door, creating massive drag on one side of the aircraft. The C-47 rolled inverted and crashed. All 4 crew members died. This was the essential cruelty of Brewer's system. It worked brilliantly when executed correctly by personnel who understood the techniques and risks, but it failed catastrophically when inexperienced crews attempted to use it without proper familiarization. Standard procedures had been developed specifically to be foolproof, to work reliably even when executed by partially trained personnel under stress. Rapid release procedures required skill, timing, and understanding of equipment behavior under extreme conditions. The Army Air Forces had never developed training programs for the technique because it had never been officially approved. Crews learned through word of mouth and direct observation, with inevitable variations in understanding and execution. Major Henshaw's engineering reports from January through April 1945 documented 15 equipment failures attributed to improper use of rapid release procedures. These included 7 cable failures where crews used standard half-inch cable instead of the heavier 3/4-inch cable Brewer had specified, 4 floor attachment failures where crews exceeded weight limits without using reinforced tie-down points, and 4 control loss incidents where pilots were unprepared for the violent pitch change during cargo release. The reports revealed a pattern common in military operations: a successful improvisation developed by experienced personnel under combat conditions becomes standardized through informal adoption, then fails when less experienced personnel attempt to replicate it without understanding the critical details that made it work. Brewer's system succeeded because Brewer understood cable mechanics from his railyard experience, because he carefully calculated weight distributions, because the pilots he worked with were experienced enough to handle the control difficulties. When other units adopted the technique based on second-hand descriptions without this foundational knowledge, failures increased. By spring 1945, the IX Troop Carrier Command had issued informal guidance attempting to standardize rapid release procedures. The guidance specified minimum cable diameters, maximum cargo weights, required pilot experience levels, and recommended training procedures, but these guidelines never achieved official status as doctrine. They existed in a grey area between field expedient and approved procedure, used when necessary, but not formally recognized by higher headquarters. The morning of September 18, 1944, when Staff Sergeant Brewer stood in that C-47 cargo bay, watching Dutch farmland rush past at 120 miles per hour, he was betting his life and the lives of his crew on knowledge gained loading freight cars in Kansas City. The bet succeeded. 18 tons dropped in 90 seconds, aircraft recovered and returned home. Supplies reached troops who desperately needed them. The tactical problem was solved through accepting risks that peacetime engineering would never approve. This is the central irony of Brewer's story, that the solution to a critical military problem came not from engineers with advanced degrees or from doctrine developed through systematic testing, but from a railyard worker who recognized that safety factors existed to be tested when necessity demanded. The official procedures that the Army Air Forces had spent years developing were optimized for safety and reliability under normal conditions. Combat conditions in Holland in autumn 1944 were not normal. Aircraft were being shot down at rates that made the risks of equipment failure seem acceptable by comparison. The question Brewer's story raises, uncomfortable for military organizations that rely on doctrine and standardization. When do field expedients developed under combat stress represent genuine improvements that should be incorporated into standard practice? And when do they represent dangerous gambles that succeeded through luck rather than sound principle? Brewer's system clearly worked. The statistics on reduced exposure time and lower loss rates are undeniable. But it also clearly violated safety principles that existed for valid reasons, as demonstrated by the crashes and equipment failures that occurred when less experienced crews attempted to use the technique. The Army Air Forces never resolved this tension. They neither officially approved Brewer's system nor explicitly forbade it. The technique existed in operational practice without doctrinal recognition, used when commanders judged the tactical situation, demanded it, quietly discontinued after Germany surrendered. This ambiguity reflects a deeper truth about military innovation, that the most effective solutions often emerge from the bottom up, developed by enlisted personnel and junior officers dealing with immediate problems, rather than from the top down through systematic research and development. Brewer died in November 1944, 4 months after developing his cargo system. He never wrote a report about his innovations, never testified before boards studying cargo handling improvements, never received recognition from senior leadership. His name appears in historical records primarily because his death required official documentation. The system he developed outlived him, spreading through informal channels, influencing hundreds of missions, saving dozens of aircraft and crews, killing others when improperly executed. This obscurity was typical for enlisted specialists who made the war work at the tactical level. The generals who planned Market Garden are remembered: Montgomery, Eisenhower, Browning. The airborne commanders who led troops on the ground, Gavin, Taylor, Urquhart, achieved lasting fame. But the loadmaster who figured out how to drop 18 tons in 90 seconds remained anonymous, known only to the crews who flew with him and the commanders who authorized his modifications. Yet Brewer's contribution was arguably as significant as any tactical decision made by senior officers during Market Garden. The ability to resupply isolated airborne units quickly enough to sustain combat operations was critical to the entire operation's viability. When that resupply failed to materialize adequately, as it did at Arnhem, where the British 1st Airborne Division was destroyed, the operational plan collapsed. Where resupply succeeded, as it did at Nijmegen and Eindhoven, where American divisions held their objectives, the plan worked. Brewer's system directly influenced the outcome of multiple battles by ensuring supplies reached troops before they ran out of ammunition or were overrun. The mathematical reality of 18 tons in 90 seconds represents more than just logistics efficiency. It represents the moment when tactical necessity forced acceptance of risks that safety doctrine would prohibit. It represents the gap between what equipment was officially rated to handle and what it could actually handle when pushed by people who understood its real capabilities. It represents the kind of innovation that happens when somebody with practical experience recognizes that theoretical limits are not absolute constraints. Every cable that didn't snap despite being stressed beyond rated capacity, every floor attachment that held despite experiencing loads 50% above specifications, every pilot who maintained control despite aerodynamic forces that should have been unmanageable, these were not miracles or luck. They were the result of equipment designed with genuine safety margins that peacetime doctrine treated as absolute limits rather than conservative estimates. Brewer's insight was recognizing that the margins existed and could be exploited when the alternative was watching aircraft get shot down because they couldn't deliver cargo fast enough. The 3 aircraft that crashed due to structural failures while using Brewer's system were tragic. The 11 crew members who died in those crashes had names, families, lives that ended because someone pushed equipment beyond its rated capacity. But the 68 crew members who died in aircraft shot down using standard procedures also had names, families, lives that ended because their aircraft spent too much time exposed to enemy fire. The moral calculation is impossible. You cannot weigh 11 deaths against 68 and conclude that one approach was right and the other wrong. You can only note that Brewer made a choice, that commanders supported that choice, that some people died as a result, but many more lived. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.